All right, welcome to part two of gas laws. Today we are going to be looking at Avogadro's law, how it relates to gases, and then look at a couple other things. We'll look at ideal gas law and all of that. Um, so I don't know that there are actually any problems in the Chem 101 homework that deal with Avogadro's law, but Avogadro's law helps us to understand ideal gas law and why we have that. So this is going to start getting into the material and start talking about kinetic molecular theory and why temperatures and pressures happen a certain way and all of that. So we'll address those couple of things first, and then we'll go from there. So the question says, state Avogadro's law. The outcomes for this unit. State Avogadro's law and explain its significance. Define standard molar volume of a gas and use it to calculate masses and volumes. State the ideal gas law and use ideal gas law to calculate pressure, volume, temperature, or amount of a gas when the other three quantities are known. So a couple of things that we'll have to note here is, for our purposes, we are going to use moles, and I'm trying to get there it goes. For us, the number of moles is actually going to be related to our mass. Remember, we can convert from moles to mass. And so when we talk about molar volume and calculate its mass and things like that, we're going to talk about how much volume 1 mole of a gas occupies. Excuse me. All right. So let's get started and look at some of these things. So the first law that we are going to talk about is Avogadro's law. And so real quick, earlier in this class, earlier in the year, what is Avogadro known for? That's right. He's known for establishing the relationship that 1 mole of any substance is 6.022 times 10 to the 23rd units of that substance. So Avogadro did a lot with chemistry, but basically he defined what the mole is. So another relationship that Avogadro has, and this is the actual relationship that we're going to be using for this one right now, is that 1 mole of a gas occupies 22.4 liters. And you might remember this when we did stoichiometry. We used this a little bit. So 1 mole equals 22.4 liters. Again, I have to stress that this is only for a gas. For a solid, it's going to occupy, for the most part, way less, depending on the density. But solid, liquid, and all of that are much more dense than gases. But 1 mole of a gas and this is at 1 atm. So 1 atmosphere of pressure, standard pressure, 1 mole of a gas is going to occupy 22.4 liters. All right. So what is Avogadro's law? Avogadro's law states that, or Avogadro's principle states that equal volumes of gases at the same temperatures and pressure contain equal number of particles. So what he discovered is that if he took 22.4 liters of a gas, of nitrogen gas, versus hydrogen gas, what he discovered is that at standard temperature and standard pressure, that he was able to fit the same number of particles in there. So 6.022 times 10 to the 23rd particles. Again, we're not going to be using Avogadro's number in this. We're going to be using the molar relationship that 1 mole is equivalent to 22.4 liters. All right, that's what we're going to be doing. So what he was able to do, just like Charles Boyle and Guy Lusset, is he was able to establish a relationship between volume and moles. So his relationship is that the initial volume over the initial amount of moles is going to be equivalent to the new volume and then the new amount of moles. All right. So this is assuming that we are changing the number of moles, the amount of molecules or amount of particles in there. So again, this is a direct relationship. So as moles increase, volume increases. We really shouldn't be looking at changing the volume. So if the amount of gas increases, then the volume will increase. If the amount of gas decreases, and by amount of gas, I'm referring to moles, the amount of gas will decrease. So again, direct relationship. So if we were to graph Avogadro, since it is direct, we're going to have that straight line. The only one that we don't have a straight line for, the only one that we have a curve for, is Boyle. All right, so here's our graph. I forgot that I put it on there. So again, this same linear relationship applies to Charles and Guy Lusset. Now, so another way to look at Avogadro's law is as the number of particles increase. So if we have 2 rabbits and they reproduce and they make more rabbits, they multiply and they multiply, they're going to take up more space. So as we increase the number of particles, it takes up more space, is all that really says. All right, so molar volume. Molar volume for a gas is the volume that 1 mole of a gas occupies at STP. Remember, STP is standard temperature and pressure, which is 0 degrees Celsius in 1 atmosphere, or as I said earlier, 273 Kelvin in 1 atmosphere. Avogadro showed experimentally that 1 mole of any gas will occupy 22.4 liters at STP. And so conversion factor for 1 mole of any gas, typically it's any ideal gas, is 22.4 liters at STP, but we can use this on there. So this is a constant, and it can be on your charts and things like that. All right. So, so if we were to ask the question, what volume would 0.881 moles of oxygen gas occupy at STP? So if we have 0.881 mole of O2, we want to know what volume will it occupy. So we know that 1 mole of O2 is going to occupy 22.4 liters. So basically 0.881 times 22.4. means that it's going to occupy approximately 19.7 liters. All right. So we can do this using dimensional analysis and all of that. We could also do it using the Avogadro's formula and say it like this. So this would be Um, so we could say volume over moles equals volume over mole. We could do it this way as well. So we want to know what volume would it be at STP, things like that. Um, so what we're actually kind of saying here is that what volume would 0.881 be if we had 22.4 liters and 1 mole. And so we can compare that, and what we would find out is if we did it this way, 22.4 times 0.881 divided by 1 gives us 19.7 as well. All right, so either way, we ended up with 19.7 liters. All right, so here are some example problems. All right, well, here's how we would approach that one. I'm just going to go ahead and show you this since I've already solved it on the other page. So what did we know from the initial problem? We knew that we were trying to solve for volume 1, how many liters. The original moles was 0.881 moles of O2. New volume was 22.4 liters with 1 mole. All right, so we set it up and we get 19.73 or 19.7 when we consider that we only had, no, we had 3 sig figs. We only had 3 sig figs. So using it, setting it up, and cross multiplying, we get 19.73. Now, if we use dimensional analysis like here, we have 0.881 times 22.4 gives us 19.73. Again, whichever method is easier for you, you can use. So let's look at this one. This question is asking a little bit different. It says how many grams of N2 will be contained in a 2-liter flask at STP. So what we're starting off with a volume. So we have 2.0 liters of nitrogen. Now, how do I get that into a number that I can get grams from? Well, my first step would be to solve for moles. I know that there are 22.4 liters of nitrogen in 1 mole of nitrogen, and that's going to give me moles of nitrogen. So now that I'm in moles of nitrogen, I can get to grams. 1 mole of nitrogen, and now I need to solve for the molar mass of this. So I'm going to look up the molar mass of nitrogen. Molar mass of nitrogen, 1 nitrogen atom is 14.01. So 14.1. So the molar mass of N2 is going to be 28 grams of nitrogen. And so we can do that and just simply solve for grams of nitrogen. So 2.0 divided by 22.4 gives us 0.0893 moles times 28 grams gives us that we had 2.5 grams of nitrogen that was produced or contained or whatever. All right, moving on. So again, you can look at it. We could have solved it using, I used dimensional analysis. So I set it up like this, and I ended up with 2.5 grams. You probably could have solved it using Avogadro's formula as well, but I just find it easier to use dimensional analysis on it. All right, so now moving into ideal gas law. We needed to establish that there's a relationship between moles and volume to make this jump. So we have this relationship between moles and volume. We also have this relationship of P1 V1 over T1 equals P2 V2 over T2. So what we want to establish is a relationship between pressure, volume, temperature, and moles. All right, so we want to be able to get all four of these things and calculate it using one problem. The difference between ideal gas law and the other gas laws is ideal gas law is only one set of conditions. And what I mean by that is everything that we've talked about before has been kind of a before and after situation. Ideal gas law is only going to look at it at one instance of time. So we're not going to have a before and after. We're just going to have one set of circumstances. So we're not going to have a change in temperature in these or a change in something. So what is the ideal gas law? What it attempts to do is approximate the behavior of gases under many conditions. It really tries to approximate the behavior of gases under ideal conditions, under the perfect circumstance. But what we've discovered mathematically is that the change from the ideal to the real is not that extreme in most cases. So here's the formula for the ideal gas law. Ideal gas law is PV equals nRT. P stands for pressure, V is for volume, N is moles, R is a constant. This is the gas constant. We are going to use 0.0821 liters atmosphere over mole Kelvin. All right, so that is our units for that. Don't think that that's a problem that you're setting up, and temperature is going to be in Kelvin. So for ideal gas law, a couple of things that we need to know is volume must be in liters. Pressure must be in atmospheres. Temperature, that's not really a change, but temperature must be in Kelvin. Moles is obviously going to be in moles. All right. So sometimes you'll hear teachers refer to PV equals nRT as PIV-NERT or even the pervert formula, just depending on how they want to measure it. But I tend to use PIV-NERT. All right. So R is called the ideal gas constant. R is dependent on the units and variables for PV and T. There are several different R's. This is the one that is given to you on your equation sheet. All right. So it's easy enough to memorize the conversion between millimeters mercury to atmosphere, kilopascals to atmosphere, rather than trying to remember four different R's. I just remember one R value and convert the other way. So just remember using PV equals nRT. Temperature is always in Kelvin. Volume is always in liters. Pressure is always needs to be in atmosphere. All right. You will change, if you change the pressure, then you have to change the R value. And I don't want us doing that. I want us using the same R every time. All right. So an example of solving ideal gas law using this. All right. So looking at this, 30 degrees, remember we have to convert that to Kelvin. So I believe that is 303 Kelvin, 273 plus 30. All right, that is, so this is our temperature, this is our volume, and this is our pressure. So we have the formula PV equals nRT. So what do we know and what don't we know? Well, we know R is a constant, so we can look that up. We know pressure, volume, and temperature. So let's go ahead and plug that in. Pressure, 3.52 atm times the volume, which is 0.05 liters, equals N, which we don't know. R is 0.0821. Yes, 0.0821 liters, atmospheres, moles, K. I just wanted to double check that one. And then we're going to multiply that by 303 Kelvin. So what we see right away is that Kelvin disappears, leaving us with liters, atmospheres over mole K. We're trying to get N by itself. So first thing that I'm going to do is 0.0821 times 303, and that gives me 24.88. So that gets rid of that on that side. And then over here, I have 24.88 liter atmosphere mole. All right. So that's going to get, so when we do this, we get rid of liters, we get rid of atmospheres, and we're left with 1 over moles as our answer. So, actually 1 over moles, which is just moles. So when we solve this, 3.52 times 0.05 divided by 24.88 gives us that we have 0.007 moles. Now, if you wanted to put this in 3 sig figs, we could say 0.00707, and then that would be our answer. All right. So again, here's kind of our setup. Did everything. So 0.0071, which is what we came up with. All right. So what I would like for you to do is go ahead, try this one on your own. So pause the video, try to set it up, identify your givens. So this is volume, this is pressure, this is temperature. R equals 0.0821 liter atmosphere mole K. And then set it up and solve. All right, so let's go ahead and look at the solution for this. So what were our givens in the problem? We knew that pressure was 1 atmosphere, that volume was 0.6 liters. We wanted to know the moles. And actually, this one asked us calculate the grams. So first we had to solve for moles, and then we got grams. So we use PV equals nRT to solve for moles, and we find out that we have 0.25 moles of N2. And then from there, we can use dimensional analysis that 0.025 moles times 28 grams per mole gives us that we had 0.694 grams of N2. All right. Now, getting into ideal versus real. So ideal is the perfect set of circumstances. Real is what happens in the real world. So an ideal gas obeys all the assumptions of the kinetic theory. I'll get to the kinetic theory in a minute. But kinetic of atoms or molecules that are non-interacting particles. So in an ideal, it says that the atoms or molecules have no attraction for each other. All right, so that there's no such thing as intermolecular forces or anything like that. What we know is that anything that has mass has some sort of gravity, some sort of attraction. We know that molecules, because of the nature of that they're surrounded by electrons, at the very least experience London dispersion forces, if not dipole-dipole interactions or even hydrogen bonding. So the shape of the molecule, the things going on are really going to determine how much that change is going to be. So no gas is perfectly ideal. An ideal is a theoretical set of circumstances. All gases take up space. All gases interact with other molecules. So therefore, there's going to be forces of attraction and repulsion. Most gases will behave like an ideal if the right conditions are present. All right. Real gases do not behave like ideal at extremely high pressures or extremely low temperatures. So another way to make this statement is gases will act ideally at low pressure because the molecules are really far apart, and high temperature. The reason why is because at low pressure, the gas molecules are really far apart, so the chances of the intermolecular forces causing them to pull together is lower. And then at high temperature, they're moving faster, so their interaction is going to be less. That's why they act most ideally at that set of circumstances. All right, so I'm going to skip this slide. That one's not that important. All right. So ideal gases do not have a molecular volume and show no attraction between the molecules at any distance. Real gases have volume and show attraction at short distance. High pressure will bring the molecules very close together. This causes more collisions. Also allows weak attractive forces to come into play. By weak attractive forces, they're talking about IMFs, which we talked about in Unit 12. That's why I did Unit 12 first. With low temperatures, it also causes the gas to come close together and experience liquefaction even. So the molecules don't have enough energy to continue on their path to avoid a reaction. All right. So one of the laws that we have that kind of goes in association with this is Dalton's law of partial pressure. All right. Basically, what Dalton says is if you put molecules of gas in a container, that if we put different gases in a container, so we have N1 plus N2 plus N3, we're going to have in total molecules of gas, and it could be a mixture of gas. What that also tells us is that the pressure of each of those gases is also additive. So if we know the individual pressures of a gas, we can know the total pressure. Or if we know the total pressure and we know two of the partial pressures, then we can find that out. And also, if we know the pressure of the gas, we can find out the number of moles as well. So Using this analogy, I have five pink Skittles, 4 yellow Skittles, 3 green Skittles, and 2 blue Skittles. I can determine the total amount. So, so I have 5 plus 5 is 10, so there's 14 total Skittles in this, if I did my math right. And so, in other words, and so we can also look at this in terms of pressure. If this represents the pressure for one was 5 atmospheres. The pressure for 2 was 4 atmospheres. The pressure for gas 3 was 3 atmospheres. And the pressure for gas 4 was 2 atmospheres. So when we put them all in one container, all of those pressures are going to add together to form a 14 pressure. All right. So again, all of the units of pressure must be the same. And Dalton's partial pressure assumes that all of them are going to act as an ideal. All right. So if we have a sealed tube that has certain gases in it, one of the experiments that we do is collecting gas over water. So you'll have some sort of chemical reaction that happens in this tube. This tube would be completely filled with water, and as the gas is formed, it's going to push the water out, and only leaving gases. So we have a gas in here, and we have water as well. So our total outside pressure is 739.6, and our internal pressure of both the water vapor and the gas, water vapor is 17.3, and then the gas, that means the gas is 722.3. So kind of what that means is if our total pressure, P total, equals 739.6, and we know that P total is equal to pressure of the gas plus pressure of H2O. So when we do this, 739.6 is equal to, if we're trying to solve for the pressure of the gas, and we can, this one can be found on a table, and it's based off of temperature. And we said that the pressure of the water was 17.3. So 739.6 minus 17.3 gives us 722.3, which is this number. All right. So there may be a couple of problems with that. We already talked about Avogadro's law. Okay. So I'm going to end this video after this one. You should be able to, after we do this, you should be able to answer most of the problems on Unit 11's homework. I am going to post one more video with this that is related to kinetic molecular theory and addresses a couple of the first couple of questions in the homework so that you can see it. Not real sure. There it goes. Not real sure why it's not. So I'll post those and go through the first couple of questions that are a little bit more just knowledge based and lecture based. All right. So we have this problem here that says NO2 and H2O react to form nitric acid and nitrogen monoxide gas. All right. Question says, what mass of water will be required to react with 15.5 liters of nitrogen dioxide? So nitrogen dioxide is this. So we want to know what amount of water is going to be required to react with it. So first thing, I'm gonna do stoichiometry. So I have 15.5 liters of NO2. I know that there are 22.4 liters for every 1 mole of NO2. All right. Now, this is going back to Unit 8, stoichiometry. So I need to establish a mole ratio. I have 3 moles of NO2 for every 1 mole of H2O. And then I want to know what mass. So for every 1 mole of H2O, I have 18.02 grams H2O. And then that's going to give me my mass of H2O. All right, so pause the video, whatever, check to solve it, and then check your answer. So I got 4.16 grams. All right, and then another approach would be what volume of nitrogen monoxide would be produced from 100 grams of water. So this one, we're going to start off with the 100 grams of water. And we have to use stoichiometry. There are 18.02 grams of H2O for every 1 mole of H2O. Then we do stoichiometry, that there for every 1 mole H2O, we have a coefficient of 1 there, we have a coefficient of 1 there, so it's 1 mole of NO. And then we know that for every 1 mole of nitrogen monoxide gas, there is 22.4 liters of NO gas. And then you can go ahead and solve, and that's going to give you liters of nitrogen monoxide. All right, so you would end up with 124 liters of nitrogen monoxide. All right, same equation. If 42 liters of nitrogen monoxide produced, what volume of NO2 reacted? So this one, you're going from volume to volume. So 42.0 liters of NO. And 1 mole of NO is 22.4 liters. And then this, we have to look at mole ratio. So there's 1 mole of nitrogen monoxide, excuse me, for 3 moles of NO2. And then for every 1 mole NO2 is 22.4 liters. Now, this one's nice because we have 22.4 multiplied there and divided there, so that cancels. So really all we have to do is 42 times 3, and that will give us our answer in liters of NO2. All right, so you would get 126 liters on this if you did it. If you want to go through and do it and do 42 divided by 22.4 times 3 times 22.4, you should end up with the same exact answer. All right, So that kind of concludes part 2 lesson. From this, you should be able to answer most all of the questions all the way through um, in the homework. Just if you see one that's a concept we haven't covered yet, skip it. I know the first few questions have not been covered. I may need to go back and cover partial pressures a little bit more, but you have all the information you need. Um, so I'll go ahead. Let me. So remember, you have combined gas law. All right, so you have combined gas law, we have ideal gas law, we have Avogadro's, which is V1 over N1, V2 over N2, or it could actually be pressure 1 over N1 equals pressure 2 over N2. And then another formula that we have is Dalton's law of partial pressure. So you had P total equals P1 plus P2 plus P3, or it could be N total equals N1 plus N2 plus N3. All right. From there, you should be able to get just about everything. Just remember that R is a constant. R is 0.0821 lattimole, liters atmospheres over mole Kelvin. And then also remember that pressure should be in atmospheres on this. Volume should be in liters. And then temperature is always in Kelvin no matter what you're using.